All right, let's dive in. We're going to talk about an idea that's, believe it or not, over 200 years old. But here's the crazy part. It's the invisible engine that powers pretty much our entire digital world. You know, the music you stream, the photos you share. It all comes back to this one beautiful concept, the Fourier series.
So, this sounds a bit like the start of a weird riddle, doesn't it? A sound, something you see in nature, and a piece of digital data. I mean, they seem completely unrelated, but turns out they all share this deep, hidden connection.
And here's the secret. They can all be described in the exact same way. Just picture waves in the ocean for a second. It's not like you have just one perfect wave rolling in, right? Nope. You've got tons of smaller waves, all moving at different speeds, different sizes, and they all add up. Sometimes they kind of cancel each other out, and other times they combine to create one of those massive, really complex waves. This idea, adding simple things together to create something complex, is called superposition. And that idea is the key to, well, everything we're about to talk about.
So, let's get into it. Our story starts with this one guy, Joseph Fourier. He was a French mathematician who, way back in 1807, made a claim that was so bold, so out there, that the scientific community at the time just flat out rejected it. Okay, so Fourier's big idea was this. Any repeating signal, and I mean any signal, no matter how jagged or weird looking, can be perfectly described just by adding up a bunch of simple, smooth, sine and cosine waves. These simple waves are called harmonics. You can think of them like the individual notes that make up a musical chord. The first harmonic is your main note, the second is twice as fast, the third is 3 times as fast, and you just keep going. So how does this actually work? Well, let's try to build something that seems totally impossible. A square wave, a signal with sharp 90-degree corners, using only smooth sine waves. Okay, so first we start with the average value, kind of a flat line. Then we add the first harmonic. You see, it's a rough approximation. Now let's add the third. Look at that, it's getting closer. With the fifth and the seventh, and on and on. Each new wave we add makes the approximation better and better. It just snaps more tightly to that square shape. It's an absolutely brilliant way to see Fourier's claim in action.
And this right here was the part that just blew people's minds. It was the really controversial bit. I mean, think about it. How on earth can you create a signal with a sharp, jagged corner by adding together a bunch of perfectly smooth, continuous waves? It feels wrong, right? It sounds like some kind of mathematical magic.
You know, an idea this radical was never going to just sail through. Fourier's work was hit with some serious skepticism from some of the biggest names of his time. It really sparked a huge debate.
So the idea of using sine waves wasn't totally new. Euler had done it decades before for things like vibrating guitar strings. But the great mathematician Joseph Louis Lagrange basically shut it down. He argued there was no way you could use smooth waves to create the sharp corners you'd get from, say, plucking a string. So when Fourier showed up half a century later with an even bigger claim, he was basically walking right into a scientific storm.
The whole debate really boils down to this. Lagrange's argument was completely logical. You can't make a sharp point with just a few smooth curves. But Fourier's real genius was seeing what happens when you use an infinite number of them. For Lagrange, this was a cute but useless trick. For Fourier, this was a universal key that can unlock how pretty much anything that repeats actually works.
In fact, Lagrange was so against it, so fierce in his opposition, that he personally blocked Fourier's 1807 paper from ever being published. Can you imagine? It took another 15 years for the work to finally get out there. So you have to ask, why was Fourier so sure he was right? What made this idea so powerful that he'd fight for it for decades?
Well, the answer isn't just about drawing pretty waves. It's about predicting how signals actually behave when they go through a real-world system like, I don't know, an audio signal going through an amplifier?
Okay, so if you feed a complex signal, like our square wave, into a system, it's almost impossible to predict what's going to pop out the other side. The system messes with it, distorts it in all these complicated ways. It's a mess. But here's where the magic happens. If you put a simple, clean sine wave into that same system, what comes out is another perfect sine wave of the exact same frequency. Yeah, it might be a little bigger or a little smaller, maybe shifted a bit in time, but its basic shape is perfectly preserved.
This special property actually has a pretty cool name. Sine waves are called eigenfunctions. I know, it's a mouthful, but you can just think of it like this. Sine waves are the system's native language. They're its favorite song. When a system hears a sine wave, it gets it. It knows exactly what to do, and its response is super simple and totally predictable.
And that is the whole punchline. Fourier analysis lets us take a super complex signal, translate it into the simple language of sine waves that the system actually understands, see how the system handles each simple little piece, and then just add all those simple responses back together to get the final complex output. It turns one impossible problem into a bunch of easy ones.
So this powerful idea, which, remember, was first thought up to understand how heat moves through a metal bar, has since wormed its way into almost every single corner of modern science and technology. It's everywhere.
I mean, forget just heat and waves. It's totally fundamental to electrical engineering, to radio, to TV, to our entire digital lives. Every single time you listen to an MP3, your phone or computer is using a fast version of Fourier's method to rebuild the sound. And every time you look at a JPEG image, you're seeing data that was squished down using these exact same principles.
For over 200 years, this one core insight, that the complex can always be built from the simple, has been one of the most powerful tools we've ever come up with for understanding our world.
And it kind of leaves you with this one last really fascinating thought. Fourier taught us to look for the simple symphony hidden inside all the noise. So what else in our world, from our economies to maybe even our own emotions, is just a complex signal, waiting for us to break it down and find its fundamental notes?